Great. All right. Welcome, everyone. Thank you for joining us. Today is a presentation on healthcare and science and technology spaces and buildings, and the ways in which embodied carbon is an opportunity and a challenge in this space. We are hosted by the BSA and as a knowledge community, as well as the Boston hub of the Carbon Leadership Forum. Rochelle Ain and I are the co-chairs for this knowledge community, and we would love to hear from you if you'd like to join or have any questions. clf.boston@gmail is definitely the easiest way to get in touch with us. There are a number of working groups active within this knowledge community and hub, as well as a growing number of resources and tools. We're working on getting these resources and tools posted to the website so that you have easy access to them. And the education series working group is what this event is coming out of. Sorry, I'm moving backward. The education series began with an event in 2019, continued on to a 101 series last year with 12 sessions covering an introduction to many, many topics, including disciplines. And the series this summer is meant to dive into a number of different sectors specifically to try to find opportunities for working together to reduce the embodied carbon footprint of our projects in the sector. There are many events happening this month. We are here around highly controlled spaces, again, healthcare, science, and tech. There is another impact series session later today on commercial and multifamily projects. And then the last two are next week, one on public projects and the other on smaller residential scale projects. We also have CLF hub meetings about every other month. The June session was pushed to July because we have all of this happening. And the other dates are here shown for reference. Again, clf.boston@gmail.com. And apologies, I don't know why it's moving backward. So with that, I believe I'm going to hand over to the instigators. Today we have an amazing list of folks joining us for a bit of presentation and then hopefully a lot of discussion, questions, and comments from everyone on the call. With us today, Andrea Love, Principal and Director of Building Science at Payette, Matthew Fickett, Architect and Director of Science and Technology at SGA, Pat McCafferty, Associate Principal and Structural Engineer at Arup, Paul Richardson, Principal and Structural Engineer at Bureau Happold, Jacob Knowles, Director of Sustainable Design at BR+A, Aurora Jensen, Sustainability Engineer at Bureau Happold, and myself, Julie Janeski, Principal at Bureau Happold as well. I think what you'll notice is that we've got a combination of different design firms, different engineering firms, and a real attempt at collaboration and camaraderie around this topic to be able to move the industry forward. So with that, Andrea, can I hand it over to you? And I'll see if I can get the slides to participate.
That would be great. Okay.
Good.
Yeah. So as was mentioned, my name is Andrea Love, and I'm a principal and the Director of Building Science at Payette. And I was just going to give a brief overview of some of the architectural impacts or things to consider that specifically when we talk about science and technology in healthcare buildings. So just to kind of touch on some of the issues to frame the context. And then we'll have a few deep dives from others. Can you go to the next slide, please? So science and technology in healthcare buildings are complex, right? And I think this is what, as we think about embodied carbon, this is really where a lot of the challenges come from. They're highly technical, both in what they need to do, but also in how they need to perform. And that can sometimes limit our ability to push and do different things with different materials. And so I think that complexity is both, what makes it interesting as a typology, I personally think, to work in, but also can kind of make it a little challenging, or I think can be where some of the unique things about these typologies come about when we talk about embodied carbon. Can you go to the next slide?
I apologize. I'm going to try a different view.
If you want, I could, I don't know if it would be easier, but I could present from my screen.
If you'd like, or if this view is okay, I can stick to this.
It's fine with me. I leave it up to others.
Great.
Yeah, so if you go to the next slide.
Yep.
Thanks. So this is for looking at the carbon of the lifespan of a research building. And this was a high performing building, so we're really already assuming we're pushing on the operational carbon. But even in a sort of high performing lab building, the vast majority of the emissions over the lifespan of the building still come from operational carbon. And historically, this is why I would say in these typologies in particular, we really have been focused primarily just on the operational carbon. But if you can go to the next slide. But I think we actually skipped one slide. If you could go back one. Yeah, thanks. But if we look in the kind of next 10 years, that critical time period that we need to reduce emissions, the IPCC says we need to reduce carbon emissions by 50% by 2030 and then get to net zero by 2050. If we look in that kind of critical 10-year period that we have, even in these intense typologies, in that 10-year period, for the buildings that we're working on right now, the majority of those emissions are going to come from the embodied carbon because it's that initial hit that we see from that. And so even in these really intense typologies where operational carbon can often dominate the conversation, in this critical period, 10-year period that we have, operational or embodied carbon, is something that we need to focus on to reduce our carbon emissions. And of course, like this university in particular, they have goals to get to net zero. The grid is continuously, getting cleaner. And so who knows what that really will look like in the future. So there's a potential, of course, that operational carbon, as it continues to go down, as we continue to push things like, cleaning of the grid, and, universities like this one have goals to get to net zero, that actually that can become a smaller piece of the pie, and embodied carbon will still remain if we don't focus on it a big part. So one of the key issues, that's okay, you can sleep there. One of the key things for both of these typologies is that they're very mechanically intensive buildings. And Jacob and Aurora are going to talk a little more about mechanical systems in these buildings as it relates to embodied carbon. But I think when we look at a typical building, often the mechanical systems aren't even included in the life cycle assessment. And I think even when it is often, viewed as maybe a smaller piece of the pie to some of the other portions. But I think in these typologies, it's really important because there is so much of it that we think about the embodied carbon associated with that, because it is a more significant portion of the embodied carbon than other typologies. If you go to the next slide. The other thing that's important to keep in mind, and Pat will talk more about this, is that these spaces are very sensitive and particularly related to vibration sensitivity. And this comes into play when we start to try to look at alternative ways to do structural systems, right? So the structural requirements of these spaces are a lot higher than other buildings where you may be able to look at things like mass timber. There can be some challenges posed in these typologies because of the sensitive nature of them. The last thing I think that is worth mentioning as a key issue is that there's a lot of requirements, particularly in healthcare, but also in labs, around the finishes and durability. So while things like wood or other bio-based materials may show up as a great kind of, strategy for embodied carbon, they often don't have the durability that are needed for some of these intense spaces. And we also, I know this isn't the focus of this discussion, but we always want to make sure that we keep in mind and think about the material health impacts as well. So when we're looking at we're not just looking at these individually. And I think as designers, we have an important role early in the design to really help our clients figure out how much do we really need to build. That's one of the best ways that we can try to reduce embodied carbon. And so often I think particularly for science and technology buildings, because of these intense requirements for mechanical systems and structural requirements, and we need bigger floor-to-floor heights, that it's just viewed as easier to build all new construction, right? And let's tear down some existing buildings and build new buildings. And the diagram on the left is showing actually for a project we're working on right now, where the client wanted to build a 100,000 square foot addition. We said, you have some existing buildings. They're not great for, they're concrete structures. They're from the 60s. They're not great for all types of research, but there may be certain places where we can kind of leverage them to use particular things in these spaces, right, that we can offload from the new addition. And so how can we kind of renovate and it still get you that 100,000 square feet that you may need, but by also using existing buildings. And a great example of this is the building we did at Tufts, where the project brief was actually for a significantly larger building, and to tear down an existing building from the 1800s, we built a smaller addition and leveraged some of the existing building to renovate it, both for energy efficiency, but also reducing the size of the building that need to be built. And then I think it's important to keep in mind, we've thought a lot about this from a mechanical strategies, but also from, I think, starting to think about it from an embodied carbon of how much intense space do we really need, right? So maybe, you know, I think that I always love this diagram because it really shows how, or this image, I should say, how simple kind of it is on the right? There's just some actuators, a cable tray, and a few lights. Whereas you can see on with the glass partition, you can see the intense nature of the systems that's required in the labs. And I think taking this further thinking and trying to understand, maybe there's ways we can do different things with the mechanical systems in this kind of lighter intensity areas than we do in the, you know, more intensive areas. And how can we kind of right size so that we can reduce embodied carbon where we can, but you know, still meet the requirements of the building. I think we skipped one slide. If you could go back. Yeah, and so the last thing I was going to say is that I think we need to find opportunities where we can, even in these typologies. So maybe you can't do a full mass timber building, but at Penn State, we were able to do cross-laminated timber for the floor slabs, right? So it still has steel columns and the rest of the system, but we could get cross-laminated timber for the slabs. We're using end-grade wood floor, and we're doing a glulam mullion as opposed to a traditional aluminum mullion. That by using the glulam mullion, we're able to reduce the embodied carbon of that framing system in half. And then I think it's always important just to keep in mind kind of an integrated design and how decisions that you make can impact other things, whether for good or bad. And then for this example, because the timber has a dramatically lower U value, because it's a lot less conductive, we're actually able to eliminate the perimeter heat. Where we wouldn't, because we have very tall floor heights, even with triple glazing, we couldn't get rid of the perimeter heat. So there's embodied carbon savings there of not needing that supplemental system. Also because we have a deeper mullion, and this is very particular to this orientation, but it's northeast orientation. It's actually deep enough now that it actually blocks all the direct light in the early morning. So we could get rid of the interior shade. So there's some embodied carbon, sort of ancillary embodied carbon savings that came from that decision to go with the timber framing system. Oh, and then, you know, working with our great team at Penn State, we're able to get to an 87% reduction in operational energy. So still focusing on that embodied, or the operational carbon as well as the embodied carbon, meeting the 2030 commitment targets. And that's everything I had.
Super.
Pat.
So thank you. I think I'll pick it up from there. So just very briefly, my name is Pat McCafferty. I run the structural engineering team for Arup here in Boston. I've been with Arup my whole career. I started back in the 1900s in London, and I've been here for about 10 years. I've been asked to talk about a really interesting joint research project that we've been doing both with Arup and with Payat about looking at the opportunities and the limitations of using something like cross-laminated timber and mass timber generally in vibration sensitive programs like labs and things like that. And so Andrea touched on the fact that labs provide a particular challenge to the structural engineering team because the vibration requirements are so stringent. And typically the way you get around that is you either increase your mass, well, you do a combination of increasing your mass and increasing your stiffness in order to get the floors to be as stiff as you can. Timber systems are not particularly heavy and are not particularly stiff. And so the conventional wisdom is, you guys must be nuts. It doesn't work there. And so we thought, well, yeah, maybe it's nuts, but let's figure out how nuts. And so the study is to actually quantify what are the challenges and to see if we can work around those. First of all, if we start with, why are we even considering CLT? There are lots of reasons why we like CLT. Everything from its carbon sequestration, the fact that it's renewable. As I say, it's extremely lightweight, which in many applications is a good thing. In labs, maybe not. It's naturally fire resistant, which surprises lots of folks, but it is. Once it's charged, you get natural fire protection. Contractors love it. We've been using it now for a number of years, and the contractors, the first time they work with it, the GCs, they're like, I can't believe how quickly that building went up. It literally flies up. It's clean, it's locally sourced. There's a lot of opportunities with prefab. Lots of reasons why we like this, not to mention the fact that just from a biophilic perspective, it's beautiful. So it's better. Next slide talks about the fact that, as I mentioned, if you advance one, back one, there we go. It's also faster. Like I said, these things can fly up if detailed properly. This is just one example of a project that was 30% lighter and was erected 5 times faster. You're able to build a floor a day. You can see between day 1 and day 6 how absolutely fast these things can go. So that's a great from a scheduling perspective. And then also it's cost competitive. So the next slide just speaks to that. It's still not the cheapest system. There is still a premium, so you have to want to use it. And we've demonstrated there are lots of reasons why you would want to. But there's still somewhere between a 15 to 20% or so premium that we're finding in the market for going to mass timber. But that's not an insurmountable hurdle. And so that's why we're starting to see mass timber come into its own. If we get into the specifics of this typology, Joe, the laboratory floors, as I mentioned, it's not particularly heavy, it's not particularly stiff, and so our study looked at a sort of prototypical floor plate. Next slide just shows you what we've assumed. Basically, we took a sort of a typical 21 by 21 foot bay, sort of a modest lab floor, but something that's still workable. Understanding that, there is a sweet spot when you're dealing with mass timber and glulam, things like that. 20 feet, you're going to start to realize the benefits of it. And we looked at basically 3 different options. We looked at a steel beam with CLT floor slab. We looked at a glulam beam with a concrete slab, and we looked at an all glulam system, a glulam and CLT mass timber system. Each one of those looked at the 21 foot by 21 foot bay. We did a lot of intensive nonlinear structural analysis to figure out what the floor response was using sort of Arup's own floor vibration analysis techniques. And we targeted sort of a reasonable VCA level of acceleration. And you can see here, this diagram suggests that when we went to the full glulam CLT system, the idea was to introduce a couple of additional secondary beams, again, to try to stiffen the system up as much as possible. The next slide shows in a little bit more detail the different types of systems. So as I mentioned, the first one we looked at was just throwing CLT with the reinforced concrete topping slab on top of it onto structural steel beams. The second one was looking at throwing a concrete slab over glulam. And then the third one is, I think, the most interesting. It's sort of a 100% mass timber, albeit with a sort of a modest reinforced concrete topping slab. There are pros and cons of each one of these systems, from weight, from overall structural depth, and frankly, from erection and construction strategies. The latter point is where we are now, which is why we want to engage a contractor in Shawmut to help us get at, well, what are the sort of the time on site scheduling implications and cost implications of each one of these 3. So the next slide shows how we were targeting the assessment. As I mentioned, we're targeting a VCA level of velocity, floor velocity, about 2,000 microinches per second. And we got just around there. We were hovering right around the sweet spot. And we evaluated each one of these options based, if you go to the next slide, in terms of both the overall tonnage and the total structural depth. And what you see here is that we're able to achieve it with some, some give and take on both of those parameters. The option, the scheme that I find most compelling, most interesting is, as I said, the scheme 3, the glulam and the CLT all timber scheme. And that's the one where we really want to start to get at, because all of these analyses have certain presumptions into things like the connectivity, the stiffness of the connections, right? It's more than just the stiffness of the elements themselves. It's actually getting at how stiff is that interface between the CLT and the gluon? How stiff is the interface? Can we get any sort of composite action benefit between the concrete and the gluon, those sorts of things? Arup has got a lot of good best practice recommendations for conventional office floor assumptions. But most, to our knowledge, no one's really tried to look at these things in these sorts of environments where we're targeting super high threshold, or low thresholds, I should say, on floor vibration. So we really want to get at that. And to do that properly, you really do need to do physical testing of these things. So if you go to the next slide, you'll see that's sort of our next step, is to actually go out there and measure these things and have a feedback loop so we can fine tune our analysis models. This is something we do regularly. Actually the photos on the left you see, that's another lab that we did a couple years ago where we want the feedback loop. We made certain analytical assumptions. Let's actually go out there and physically test this. We send Arup's advanced technology folks out there. They measured the floor vibrations, and we calibrate our tools. In this example, we found that we got it spot on. We want to do the exact same thing with this sort of study too. And as I say, that's our next step.
Pat, thanks very much. Jacob, over to you.
Great, thanks. Very exciting stuff. All right, so let's jump off of Andrea's point about MEP systems in lab buildings having higher embodied carbon. You can probably guess from this image that it would have more embodied carbon. Go ahead. So we looked at a typical core shell developer lab building, including both the base building and the fit out, and did our best to calculate the embodied carbon of all the MEP systems in that building, and then compared that to typical benchmark data on embodied carbon for an office building. And you can see the comparison on a kilograms of CO2e per square foot basis. You're looking at multiple times what a typical office would be for the MEP systems. The breakdown of that is shown here. This is all the components that we took into account. And not surprising, the mechanical is the biggest driver, more than the electrical and plumbing, although those are key components also. And then within the mechanical, the big drivers are air handlers, ducts, piping. And then you can see at the top of each category, we've got the fit out, the ducts and piping, and then in electrical, we got the electrical fit out. And so you can see the base building systems are a huge driver. They carry up a lot of the physical weight of all that material. And then as you do multiple renovations and upgrades and new fit outs over 60 years, that's going to compound. Now, we might have been a little aggressive in our assumptions of how much actually gets replaced over the 60 years, but it could be somewhere in that range of nearly doubling the embodied carbon, because the structure stays, right? But the MEP systems get replaced and upgraded over time. So that means that the embodied carbon of the MEP systems on the life cycle is even greater. And so one of the other things we wanted to look at is, well, okay, so we all talk about higher performing lab designs, right? So using chilled beams instead of all air, for example. And we wanted to make sure that that proved out, not just in terms of operational carbon savings, but also embodied carbon savings. And we did a comparison of a conventional all air core shell developer lab versus a chilled beam one. And you can see that with the major reduction in air handlers and ducts, there's a significant savings on the embodied carbon. Granted, it's not a game changer, right? You might be targeting close to carbon neutral for operation, and you're only getting a 10 or 15% reduction in embodied carbon of the MEP systems, but at least they're both headed in the same direction. And so I think overall, this really drives home the point that MEP systems do matter in terms of embodied carbon for these more intensive buildings.
Hey everyone, I'm Aurora. I work at Bureau Happold as a sustainability engineer, and I run a lot of our whole building lifecycle assessment. These are some best practices we wanted to put in front of this group that we're starting to construct around MEP and how we can think about this in science and tech projects. So I think, as Jacob's slides really illustrated, the replacement and repair of these components is a pretty necessary piece. I think this often gets left out of early embodied carbon estimates because A1 through A3, which are those very early stages, are the easiest to estimate, and replacement and repair requires either duplicating those early stage impacts or using a tool that can cover all of the life cycle stages. But consideration of replacement and repair against system type evaluation is a big opportunity in this space. Evaluation of refrigerants is partially an embodied carbon problem, but it also interacts with the operational side in huge ways. But I think at Bureau Happold in particular, we've been putting a lot of emphasis on evaluating alternative and natural refrigerants as opportunities on our projects, often looking for like GWP of less than 50, looking at our refrigerant volumes, as well as examining the leakage rates. So refrigerants tend to have leakage both during the installation of the equipment, during the life of the equipment, and then also at end of life when that system maybe gets dumped in a landfill. So thinking through what that might mean in terms of deconstruction or reuse of these systems could be huge in changing that picture. Design for material efficiency. I think this is really nicely represented in the example Jacob just showed. But if you're able to examine the difference between horizontal and vertical primary distribution, decoupling your cooling and heating from ventilation, that's not a universally true rule. You could imagine situations where that goes the other direction, but largely, minimizing the size of your air handling units and your ducting systems tends to have gains. And then finally, like best practices in operational carbon as well, right sizing your total airflows and evaluating your heating and cooling loads taking a pretty hard look at those can substantially provide opportunities for reduction. And then in terms of actionable pieces, I think asking our manufacturers for product specific EPDs is huge. Even industry wide EPDs. For anybody who's not aware, an EPD is an environmental product declaration. And it's a document either produced by an industry group or a specific manufacturer that provides the environmental impacts across a number of categories of the kinds of equipment we'll be putting in our buildings. These are more broadly available in the structural and architectural space, but as we press on the mechanical evaluation and we build out that database of product-specific EPDs, this will give us more leverage to use manufacturer selection and our specifications and procurement as a method to drive down our impacts. CIBSE TM65 is a standard that recently came out in Europe, and we're hoping, and Bureau Happold is part of a working group with many other peer firms to help translate a version of this for ASHRAE. The idea here is really to figure out a way to evaluate embodied carbon when EPDs are not available. So CIBSE TM65 provides manufacturer forms that you can send to your manufacturers to get a list of the respective masses within a piece of equipment, or the subcomponents in terms of emissions. Perhaps it's not formalized into an EPD yet, but you'd like the manufacturer to report what they do know back to you. So that guidance is really helpful for kind of filling in the gaps before the data completely comes through. And then finally, we hope you all stay tuned for the MEP 2040 initiative. This is an emerging working group in the industry that seeks to provide guidance around how quickly we can drive down embodied carbon impacts in MEP. A light challenge to the structural 2050 initiative, I see. So, next slide. I think the last thing we wanted to share here as another layer to Jacob's analysis is this also does interact with healthy materials. Also an emerging area, but health product declarations can help us understand what other toxicity concerns and kind of red list items might be present in our material selections. So I think this is another thing to request from our manufacturers and something to evaluate, particularly when we're looking at lab buildings that have so much in terms of quantity of these systems in the building.
Thanks, Aurora. I'm going to stop sharing. And we do have a sort of a cozy size of a group today. So if you would like to turn your cameras on and join the discussion, the rest of our session is discussion based. I'll take the last couple minutes at the end for a brief wrap up. And again, because we've got a relatively medium-sized group, if you'd like to jump in and ask a question, you can post it in the chat, raise your hand with the raised hand function, raise your hand on video, or just take yourself off of mute and jump in. I'll kick the conversation off with a question to Matthew on the mechanically intensive side of things that we've heard quite a bit about. One of the notes in the MEP best practices is to attempt to, quote, right size the mechanical system in healthcare and lab spaces. And I know that you have some ideas on where designers might be able to take advantage of that idea.
Yeah, lots of ideas. Let's see where to start. One of the first ones is just agreeing on what we think the right amount of air for a lab is. Lots of folks treat as gospel that 6 air changes per hour is the code minimum for a lab space. That's one question that I think is not quite as straightforward as it seems, and I'd love to hear from the real engineers on this call about what they think of that. But there's a bigger problem I encounter in the developer-driven world, which is that people are used to quoting CFM per square foot. And that is usually way more than 6 air changes. I was in a project meeting recently where the engineer, without trying to throw engineers under the bus, was preparing to put 2 CFM per square foot into the lab spaces. With a 9-foot ceiling, we need 0.9 CFM per square foot to hit 6 air changes. So we're looking at more than double the target there. And the developer's like, well, my broker tells me everybody's just looking for 2 CFM per square foot. And if we show them 0.9 CFM per square foot, they'll walk away and they just won't think it's a real lab building. So we're on the verge of oversizing the mechanical system by more than 100% just to hit what brokers are used to putting in their brochures. So there's an education problem out there about what our target actually should be. So all that has to do with what goes in the lab space, right? And then the other goes to Andrea's slide of make the lab space smaller. As a lab architect, that's not usually my pitch, but there's often a lot of stuff inside that lab boundary that doesn't need to be. And the tighter you can draw that, the less energy it uses, the less air it uses. And for the lab's functionality, the more air you have left over. You want 5 fume hoods, well, shrink your lab a bunch and you've got the air budget for your hoods now. So, Jacob, I've asserted enough things. You're ready to.
I'm ready. That's awesome. Great series of questions. So in terms of the minimum air change rate, typically we make sure we at least provide the capacity for 6 air changes in the zone, but not every zone has to be at 6 at the same time. So if you have air acuity, for example, and you're monitoring air quality as a belt and suspenders approach, you could purge at 6 in, say, 2 or 3 zones in the building at the same time, but everything else can be running at 4. And so then you can size your central air handlers for that lower capacity and save a lot of embodied carbon and operational carbon, and budget to invest in more efficient heat recovery and other things. Then, of course, you got the developers, right? So can I share screen?
Yeah, if you can't, let me know and I'll make you a co-host.
Yeah, it says disabled.
Got it.
There we go.
Does that work? Cool.
Yep. So this is not totally up to date, but this is a sample we looked at about a year ago of our projects working with core and shell developer labs. And these years are the construction start dates. And each dot is a project. And the red ones are all air in the lab and all air in the office. We're really not doing that anymore. Those are kind of legacy projects. The green ones are all air in the lab, which is 2 CFM a square foot typically, and fan cooling units or chill beams in the office areas, typically around a 60-40 split between lab and office. And then the blue ones are where we've finally convinced the brokers and the developers that we can do fan coil units or chill beams in the lab and the office and reduce the CFM in the lab, in many cases, down to about 1.5, which still is a lot more than 6 air changes, but it's better. And you can see then the blended CFM a square foot trend is going down significantly. Now, it's likely to plateau because, again, they want to be able to sell to any potential tenant, and flexibility is king. But certainly going from 1.7 down to around the 1.1 range is a huge savings in terms of cost and embodied carbon. So I think that dam is breaking finally.
Jacob, while you're talking, I have a question for you. I noticed on both the stacked charts of embodied carbon for building systems that I've seen on the screen, HVAC plumbing weighs more heavily than ductwork by a substantial margin. But we're over here trying to get rid of all air systems. Are we really making everything better?
So the trade-off is if you combine the air handlers and the ducts, then that's a much bigger piece than the piping. And so if you can do more hydronic distribution, you're not just saving on ductwork, but you're saving on the air handlers, and that gets you a big net reduction overall.
Excellent.
Cool. Kirsten also has a question in the chat, and I'm posting a note to say that the CLF is hoping to have some announcements on the MEP 2040 initiative soon. If you'd like to join the CLF Boston Hub, please send a note to the Gmail address because we'll definitely be sharing that information to that mailing list as well. Super. I don't see any other hands. Paul, over to you. Oh, Jacob, go ahead.
I was just going to say, I really appreciated Aurora's presentation about what we can actually do at this point in terms of MEP systems and labs. And just to say how frustrating that process was of putting together that embodied carbon analysis, where I think literally the only manufacturer that even knew what the hell we were talking about when we asked them for an EPD was Trane, the chillers. That's the only EPD we got for the entire building. So everything else was us just getting weights and types of materials and translating that ourselves. So we definitely need the industry to put their foot down and say, we demand this from the manufacturers, so we're not having to figure it out from scratch.
Yeah, completely agree. We've got like a template email we've started sending to all of our vendors to ask both on the structural side and the facade side, but also on the MEP side. And as we were, BH has this open source tool, Jacob, that you know about for an LCA toolkit. Aurora, if you wouldn't mind putting the link to that in the chat for everyone. It's meant to be, co-creation, industry-wide, open source, so that we can all benefit and move forward with the embodied carbon work. Because the MEP world has so little information, we were starting to look at databases like the occupant database in Germany and needing to figure out how to translate the information from German and different metrics over to what could be used in the US as a proxy for MEP systems. So there's it's like the level of quality control on the MEP information available is questionable at best. But there's a real enthusiasm and interest, I think, in so many firms to be able to figure this out. So if you do have an opportunity to ask manufacturers for EPDs or for a breakdown of the materials in their equipment and or for information on what they're planning on doing for next gen refrigerants and how soon those are available, those are definitely some of the key questions. And a recording of this presentation will also be made available online. So if you didn't have a chance to jot those questions down that you can ask your MEP engineers, that's something that you can take a look at later.
A question about when we estimate, and by we, I mean you find people, estimate embodied carbon from manufactured objects like an air handler, you're talking about material weights and knowing the carbon of their production. But if I take something like, say, a sheet of stainless steel or galvi, and then stamp it, form it, turn it into a fan blade, bolt it to a motor, there's a fair amount of energy involved in that production that you can't capture from material weights. Is there any guess at that value, or is it likely that all the manufactured objects are actually significantly more embodied energy than we are suspecting?
Yeah, I wondered about that. It was funny, even when we were just taking the weight that we got from all of the subcontractors, because they give you pounds of sheet metal that they're installing and all that.
Yeah.
Even when we translated some of those numbers just by weight and the embodied carbon of that typical material, some of the numbers we were coming up with were just, it seemed unbelievably high. And we had to do some benchmarking and think about, okay, well, how much more weight is there realistically in a lab building for this material versus an office building, and look at some of the office studies that have been done and try to calibrate the answers we were getting, because some of them seemed unbelievably high. And that wasn't even accounting for all of the added energy of the manufacturing of these complex systems. So I think it's quite possible the numbers are even higher than we all realize at this point.
Great.
Yeah.
That was the part that I thought was most interesting about that study, actually, was the comparison to the office building, because there's not a lot of studies, but there's a few that kind of talk about, like, this much is typically MEP and interiors and structure. And so you can kind of like get a sense of what that typical office building is compared to those other studies. And we just intuitively knew it was more, but I thought it was really interesting just to see how much more it really is.
Yeah, I would completely agree and echo that concern. I think the fabrication piece can often be missing if we're using bulk quantity estimates, but also something like very small components that are insignificant by mass, like a controls mechanism or something, but could be significant, like adversely impactful in terms of its consequences because it's like a rare earth mineral or whatever it might be. That often doesn't get covered or captured with the proxy method of using like respective masses. I will say there are specific numbers. There's like a ton of data sets out there that have like dribs and drabs of MEP information. Like we've started to do a coverage map of kind of where some of these data points are available, whether it's generic industry points. Like there's a US data set called Quartz, where they do provide like a galvanized steel duct, EPD, although it's not for a specific manufacturer. It's a general data point from a European data set called Gabi. So there are examples where you can capture that fabrication stage, but it's different. Like the coverage is variable across the whole space.
To build on that, with the MEP 2040, which I'm super excited about, how do you are you starting to work with manufacturers to get that data, to get the EPDs and to really, try to push for that? Because I think that for the MEP system seems to be the biggest gap in the industry, is just the lack of information, as it's sort of been mentioned.
I would say, Andrea, the answer to that question is that everybody involved in that initiative is asking, and the continued onus to ask and the ability to figure out where to put all of that information is at the top of the list of the action items for that group to sort out. I think similar to the 2050 group for structure, and I think Mike is on the line, or he was. Oh, nope, there he is. We're trying to draw parallels between the initiative, the 2050 initiative, to learn some lessons on what worked really well for them and what didn't, at the same time as trying to hit the ground running as fast as possible, which means we just won't have everything done and pulled together, but rather, and ask for everyone to make a commitment to work on it and try to crowdsource the effort.
I feel like we should have a summit between the AIA 2030 commitment, the MEP 2040, and the SE 2050, and get all, because, you need to, I think to get that information, you need to leverage, everybody asking, right, and doing them in concert. And I know 2030 and 2050 have had some conversations, and so clearly we need to start looping in the MEP folks. But I think we need a summit on how can we get this industry wide as quickly as possible.
Yeah, Mike and I are trying to schedule a SE 2050 MEP 2040 chat to get that going. And we'll follow up with you and Architecture 2030 to continue the conversation. The MEP 2040 is definitely trying to build off of the Architecture 2030 so that the operational carbon target is still aligned to the 2030 mission, whereby 2040 is like accounting for the fact that the embodied carbon conversation is quite behind on the MEP side and trying to figure out what the right timeline is for the market to catch up.
I wish Connor McGuire from Columbia was here, because he would make his great point about, we just got to get these manufacturers using renewable energy, right? If it's not necessarily that one material is evil by definition, it's that their process is carbon intensive. And so there is an opportunity to solve this problem at the manufacturers end of the spectrum.
Yeah. Paul, you've got your hand up.
Yeah, I was gonna ask a question about sort of structural discussion that you started, Pat. It's going to be along the lines: how do we increase or encourage developers and clients to use mass timber more? And I think, and I've got my own thoughts on sort of the answers for that. But I think one of the key things that I've used, your study was on a modest grid. And I think that is where the key thing for me is. How do you see that we can challenge clients and brokers to recognize that a 21 by 21 grid is as real, is okay, rather than the standard sort of 30 by 30?
Yeah, I think you're right. I think it's a step change in the cultural acceptability of things. I mean, I love the image you showed, Andrea, of, you've got the intensive lab space, and then you've got the very quiet sort of study space to the right. Like, that's all you need, folks. Columns aren't evil. They're not evil. And so if we can work within those constraints, suddenly you open up so many different possibilities and opportunities. We just got to change our thinking.
So Pat, I'm curious, actually. I think there's a really interesting intersection between that diagram Andrea showed and some of the floor studies you did. In the same way that we don't need to provide 6 air changes across the whole floor plate, I'm not sure we need to be providing stiff floor plates across the whole building.
Yeah.
We'll get the same response from the developer, right? They want flexibility. They want people to be able to put it anywhere. But we're converting millions of square feet of very old buildings into laboratories. And we all look at the plans and we're like, oh, the lab definitely goes over there. It just wouldn't make any sense to put it over here. So why, when we build a new building, do we just have to draw a giant square and say the labs could go anywhere in the next 100 years? Who can know?
You're absolutely right. I mean, to me, the biggest killer in efficiency is this idea of flexibility. I understand the flexibility is the new buzzword, right? Everybody's talking, and I get that. I would counter that. I think the real sweet spot isn't flexibility, it's adaptability. So make the systems that you design adaptable, so that if you do have a change of program at some point in the future, you can easily go in and strengthen or stiffen or whatever you need to do in a very targeted, specific approach, rather than just say, sky's the limit, go wherever you want on day one. That's pretty piggish.
Yeah, I think it's also about flexibility, defining what flexibility is, right? Because flexibility doesn't mean that you need to do anything everywhere. It means you need to do anything somewhere, right? And so to Matthew's point, if there's a certain part of the building that inherently has that greater, structural rigidity, like that's where you do that kind of work versus, like you can zone the building. I think it's something that we've started to do in MEPs more from an operational carbon side, but hasn't really entered the kind of structural conversation as much, that I think would be interesting to start to think about, like, how can you zone the building from a structural standpoint to see if there's things that we can do.
Absolutely.
We've managed to do that quite successfully at our building at Harvard, the Science, Engineering, and Applied Sciences, where we had that challenge where we had areas where the vibration couldn't meet the requirements for that. So we concentrated and focused it into areas in central to the building. And then we also knowing that there was potentially some changes, we had details for adaptability to expand those areas if areas needed to be like retrofitted to be strengthened. Admittedly, that's still, it's not all mass timber, but I think that principle can work. And I think that obviously that comes back to perhaps it's a client education piece. It's like, what do you really want? I think we need to be quite bullish when we're talking to clients, when we're coming in and doing our basis of designs and such like, to say, well, actually, you can do this. you can meet all your targets, and you can still have that flexibility or adaptability that you want in the future. It's mainly the brokers that are driving that, so perhaps we need to be pushing them to say, like, this is the best thing. And it can, and from a sort of a first cost, it can be quite efficient as well. So they should be able to see that, because they recognize dollar signs.
Absolutely.
So let's push it by that and be quite bullish at that early stage.
Absolutely. And it's sometimes, and you're right, it's in education. Many times, if you can get to the end owner, end user, they're totally happy with that. And so we don't need that. This is perfectly acceptable. If you say I can go 90% of my floor plate at just dead center of this longest bay, I can't, okay, not a problem. But you got to be able to get to have that conversation. And as you say, you've got to, it's the brokers you got to educate. And as you also say, there's a cost savings, right? So it just makes intelligent sense, but it's a design decision. You need to have, we can't make those decisions in a vacuum. We need to be having those conversations with users.
And I was interested in your preferred option 3 for the floor slab assembly. It looked like there was CLT on the bottom of the beams, and I assume that greatly increases the stiffness. You're making a big fat I-beam.
Well, so what's interesting is that when you're talking about these floor vibrations, you've got what we call resonant vibration, you've got transient vibration.
Yep.
The real challenge in these systems is actually the transient vibration. And so what we find is, while yes, you get the increased overall depth by doing that, that's solving the resonant issue. The transient issue is more about getting stiffness high up, where basically where your shoe heel is exciting the floor. That's where you need to get the sweet spot. And so that's part of like the refined next step in that study, to figure out where precisely that lower level should be. Should it be actually butt ended to the bottom of the beam? Can we actually move it up or down? Because it's a tricky thing, because you're dealing with both these two different paradigms of vibration. I say that one's the one that intrigues me the most. Not necessarily because I think it's necessarily the most efficient, but because it is the all mass timber solution. And so if we can crack that nut, that's really, really cool. And if we can find some way of taking advantage of those cells, those natural voids that are being created between the lamps, so much the better. Like if we can actually compress the SMEP sandwich and take advantage of those voids, I think that would be really, really pretty slick. So lots of exciting additional things to study coming out of this initial investigation.
Yeah,
Jacob's got his,
give this
okay,
to-
go ahead. Matthew and then Jacob, and then I'm going to take over.
Okay, the reason I ask that question is adding new material to the bottom of a structural sandwich looks like a very adaptable future renovation. If you need to, you can, it's not completely easy, right? But it's a lot easier than trying to replace an I-beam. So that gave me some optimism that you could convert from a floppy floor to a stiffer one later if you needed to.
There are practical implications there too that we need to be cognizant of. How do you, because we like to maximize the size of those panels. So how do you actually get those in a future adaptation, even
Yeah.
from on day one construction? Are we building those bottom panels, putting the glue linings, and then putting the top panels? These are the subtleties we want to get at with contractors.
Mr. Knowles.
I was just going to ask if, Pat, if you were taking into account any impacts on floor to floor height, if the beam depth was getting really deep and it affected.
Yeah, we
floor.
are. And that's why the two things that we're studying are overall depth and tonnage. The third thing we got to get at is also cost. And that's part of this next step. But yes, the overall depth is important, because if you raise the floor, the building height, now you're adding more facade, et cetera, et cetera. So.
Right.
Super. All right. I'm going to take a minute to do a wrap up here and say thank you again to all of our esteemed presenters, instigators, panelists, and all of you for joining us. I took some notes. If you have any others, please do drop them in the chat. Feel free to send an email as well, in terms of what some next steps might look like and where the CLF Hub might be able to continue to help do some work in our community. So number one, ask engineers and manufacturers to pursue EPDs and next-gen refrigerant info. Lisa put a link to the building transparency site where you can download a template to use. And I'm putting a note here on an email that we've been sending to all of our vendors to ask about refrigerants as well. Happy to have you take that up as a template. Join in the MEP 2040 initiative when available, and obviously we'll pull together some sort of summit to align and join the CLF Boston email group if you would like, clf.boston@gmail.com. Address demand for flexibility and marketability in the marketplace, which seems to be a really important target, not only for structure, but also for mechanical in terms of the basic assumptions that every broker is used to talking about and doesn't quite know how to handle something different. And then Andrea and Aurora both touched on material health as a crossover item, super important. Didn't quite get to that, but hopefully something that we can dig into more in some future sessions. Again, we've got another session this afternoon, 2 next week. Metropolis, Architectural Record, and many others are tackling embodied carbon. And some of those events are on this calendar for reference. All of the signups for the 3 additional impact series are on the BSA Knowledge Community website. And if you want to join the CLF Boston Hub roundtable group, we meet again every other month, usually. July is an exception. And these are the dates for the remaining sessions this year. The email address again, to join us, the link to the knowledge community here to get to our page on the BSA website. And thanks again to all of you for joining, and to Andrea, Matthew, Pat, Paul, Jacob, Aurora for adding all of your expertise. Have a great day, everyone.
Thanks, Julie. Great work putting this together.
Thanks.
Thanks. Bye.
Thank you.
Thank you.
Thank you.
Thanks.